Without resilience, nothing else matters. レジリエンスがなければ他は何も同じという題名で、ヨナさんに、発表いただきます。Yeah, please start.
Can you hear me when I speak like this? Yeah. So how many of you? Let me rephrase. I'm sure most of you would like to go to production with a system that is like beautiful, scalable, highly concurrent, responsive, resource efficient, loosely coupled, yada yada yada. You know. We all do, right? But guess what? None of that matters unless your application is actually up. Unless it's actually available to serve the users and to provide all these nice features. Really, without resilience, nothing else matters. It starts and it ends with resilience. And this talk is sort of an exploration what resilience means. We'll go back to the definitions. We will try to learn a little bit from other sciences how they are managing resilience and see how we can apply that to software. So most of you probably, at least some of you probably recognized this song. No, that was the theme song from the Rocky movie. Rocky movies are this series. You have this underdog. He gets a shot at the title in the first movie, and they call him, the media make a big thing out of it. They call him the Italian stallion, and he sort of. He actually doesn't win, right? But he limps, really like fights his way through it. And then one of the most memorable quotes from this movie is this one. I don't know if you can turn the audio on again.
How hard you hit. It's about how hard you can get hit and keep moving forward. How much you can take and keep moving forward. That's how winning is done.
So yeah, we all know Rocky, right? Or Sly, Sylvester Stallone, right? The problem is that what it says here is really the definition of fault tolerance. It's actually, you get hit, you survive for some time, you limp along. Eventually, hopefully, you will win, but often you don't, right? This is fault tolerance, and the problem is that fault tolerance is not a sustainable strategy, long term, right? What we need is resilience. Resilience is beyond fault tolerance. Resilience is it's really the essence of what I'm going to talk about in this talk. What it is, why it's needed. What we can learn from other industries, etc. So, how is resilience defined? Yeah, by Merriam-Webster is defined as the ability of a substance or an object to spring back into shape, the capacity to recover quickly from difficulties. It's not just to limp along like Rocky, but to heal, to fully heal, or to fully restore full functionality. Not just survive, right? We have done enough of survival in our industry, I think. It's really time to embrace resilience at its full, and really build systems that heal themselves and can continue as nothing had happened, essentially. And software systems today are incredibly complex. These are just a couple of diagrams that are sort of been floating around, or images that are floating around on Twitter the last six months from the Netflix and Twitter architectures, and we really need to study resilience in complex systems because software today is incredibly complex. But the question then is what is complex and how is it different from complicated? This is a complicated system. It usually comprises of many different parts, all different, in which each sort of part has a unique role in the machinery, plays its part in the machinery, and it's really possible. It might be hard, like in this image here, but it's possible to fully understand a complicated system if you are an expert. Okay? So what is a complex system? Then complex systems are usually made of many similar interacting parts. It's like in their behavior, in how they interact together, that produces globally coherent behavior. And it is, by definition, impossible to understand a complicated system, or sorry, a complex system. You can only try to understand it by understanding its underlying rules. Just like in this example, game of life, it has very simple individual rules. It's very easy to understand it in isolation, but once you start putting things together, it becomes immensely complex. And it's almost impossible to predict what's going to happen. So it's really important that complicated is not equal to complex. And this is probably one of the most important wisdoms in this talk, and this is what I learned when I did research for this talk. It's from Richard Cook. He is an MD doing research and study in resilient systems in healthcare, and where patients might actually die and will not self-heal in many situations, right? So it's more severe than software. And he said the complex systems, they always run in degraded mode. Complex systems always run as broken systems. In a complex system, something is always failing somewhere. That's a fact. We just need to fully embrace that, right? And this means that we need new ways of thinking, new ways of dealing with it, right? To cope with failure. And the problem is that humans generally just makes it worse. So this is a great quote from Dontella Meadows. She's been doing a lot of research in systems thinking. And she writes, I quote, "Counterintuitive, that's Forrester's word to describe complex systems. Leverage points are not intuitive. Or if they are, we then as humans, we intuitively use them backwards, systematically worsening whatever problems we are trying to solve. It's extremely hard to intuitively reason about complex systems. That's the problem. And this is why I think we need to really good models and good strategies how to deal with it, because, as I said, it's unintuitive. And sort of one of the most fundamental lessons that I've learned the hard way, and also the points in this talk, is that resilience is by design. Resilience is nothing that you can just bolt on afterwards. It needs to be part of the application architecture, the way you design and build software from day one. It's extremely important. This photo is from a home in Gilchrist, Texas. It was designed to resist floodwaters. It was one of the few houses in the whole city that survived Hurricane Ike in 2008. It's a house that's built with resilience in mind from the start. So let's look now at some patterns and strategies for how to manage failure, and also how some other sciences manages failure and what we can learn from that. So starting with resilience in biological systems. I had a lot of fun doing research for this talk, and I actually started exploring things that I haven't done before. For example, resilience is in biological and social systems, also in environmental systems. There are many interesting, actually in war situations as well. I can't cover it all here, right? But I'll give you a couple of very interesting examples that I think applies very well to software. Okay. So one of the interesting stories I learned was from a great TED talk. I encourage you to go and watch it. I mean, that talk gives this story a lot more justice, but I'll try to recap it for you here. It is a story by Nicholas Peroni. He's doing research on animal colonies, right? Many animals are very social, especially meerkats. They are extremely social. So this story is about some meerkats. By the way, you have the link to the talk here, and I have a lot of references in the end if you want to really dive into. Meerkats, they're they're more than just cute, and funny. I have this thing for meerkats. I think they're really cool, but they are extremely social animals, right? Rich social behaviors. And one really interesting thing is that in a colony, it's only the dominant couple that can have babies. All the other ones are supposed to be servants, like babysitters, for all the kids that they are producing, essentially. And in this example, a GPS tracker was put on the dominant female. And you know, the dominant female, she is the one that leads the group. So she was leading the group from one feeding place to the next feeding place. And there was a big road between. And the interesting thing that the researchers discovered was that the female led the group to the road, and then she stopped. And then she gave way to the subordinates, to all these servants, so to speak, to let them try to cross the road safely, right? And if they did, if they made it to cross the road and didn't get hit like by a bus or like was run over by a truck, then she decided, okay, it's safe, and she moved the whole colony over, right? So it's really, and the interesting is that it's like nature have sort of produced this behavior over thousands of years. Like where the dominant female, she's too important to the group to have her be killed, you know, to lose her. That's why she's delegating dangerous things to less important meerkats. So, and Nicholas Corona sums up his TED talk with this in 3 words: in the animal kingdom, simplicity leads to complexity. Simple individual rules, essentially, if you go back to complexity theory, leads to complexity, which leads to resilience. Okay, I think there's a lot of things to learn there. I mean, the nature is using complexity as a strength here. The unpredictable patterns and things like that falls out of complexity. The other example I want to talk about is resilience in social systems. And this was from an article that was sent to me by a friend that's doing research in social systems and environmental systems. The paper is called "Dealing in Security: Understanding Vital Services, How They Keep You Safe," and it essentially outlines that there are 6 ways we can die, we as humans. We can die by, and these are the pie slices in this diagram here. Either we can die by being too hot or too cold, or from hunger or thirst, or from illness or an injury. Okay. Then there are 3 sets of essential services that keeps us safe, that keeps us from dying. That is shelter. That helps us from being too cold and too hot. It's supply that prevents us from hunger and thirst. And it's safety that provides us from illness and injury. And these services are laid out in layers. I mean, starting from the innermost center here, you can see we have ourselves, the individual, and then we have layers of protection that protects us from dying. Going from top down, like in the world, for example, we have things like energy markets, food markets, things like that. The country, we have the military, in the town and so on, we have hospitals, we have the police, and in the neighborhood we have like local food shops, we can go and buy food and stuff. In our home we have, the roof over our heads, we have heating, we have the refrigerator, we can store food, and with like toilet, tap water, all these things, all the way down into the individual. And so this is really how the world works around us all the time. We have these layers of protection, layers of defense that protects us from dying. And I'll get back to this when I talk about software in a second, right? This is what I call, if we give you a glimpse, this is what I call the onion layered failure architecture. And how you can layer your software this way. We'll take a deeper look into that later. So what can we learn in general from biological and social systems? That they all feature diversity and redundancy. And they all, systems with many components, have a way of having some components take over from others when they fail. They don't put all the eggs in the same basket idea. So some services can compensate for failure in others. These systems also, they have a very interconnected network structure, wide distribution across all scales, and the capacity to self-adapt and to heal itself. Usually through very simple patterns, but when applied across a wide scale, it proves to be very, very powerful and gives the system a way to heal itself. from the inside. So this brings us to resilience in computer systems. Okay? Unfortunately, we often react like this, like first not at all, and then with complete panic. And I really think that we need, as engineers, we need to fundamentally change the way we think about resilience. We need to, you know, failure is inevitable. It will happen, regardless if you like it or not. It will happen. Okay? It's better to be prepared and to manage failure. And the best way of doing that is like thinking about failure as nothing exceptional at all. I mean, failures are called exceptions in Java and Scala. Right? I think it's just wrong. It's nothing exceptional about an error at all. And if you think about failure like that, if you think about failure as something that it's just a natural state in the application lifecycle. If you have like your FSM, your finite state machine, you might boot up the application. You go to start. You might be suspended. You might be stopped. If you think about failure as just another state in the state machine, you end up in a failed state. No big deal. You plan for it. You know exactly how to get out of the failed state and continue. When you will lose less sleep this way. Trust me. I mean, if you have prepared to manage failure from day one. And one philosophy is the let it crash. If you use Akka and Erlang and others, you know that it fully embraces the let it crash idea. So I'll also dive in a little bit what that means. It is one great paper on this topic is called Crash Only Software. And is by a couple of guys called Ken Day and Fox. I have all the links at the end if you want to take a photo of that or whatever. I can share the slides as well later. But in this paper, they state that crash only software means that you crash safely. That's equal to stop, and then start is just recover fast. And this way of thinking is very simple, and read the details in the paper to understand all the intricate details, right? But the idea is very simple. This gives you sort of a sledgehammer, you know, that you can sort of solve problems, brute force in a way. Problems related to inconsistent state, for example. The application might be in some weird state or something like that, and just killing it and rebooting it might solve the problem. And they take this, even more interestingly, they take this idea further in this paper that they call recursive restartability, turning the crash-only sledgehammer into a scalpel. And the interesting thing is that they take this idea of crash-only software and applying it recursively throughout the system, from the finest grain components all the way up to the whole system, how the system scales out, and so on, from the finest grain detail all the way up. And this really gives us the ability to gracefully tolerate restarts at any level in the system. Very simple idea. If something goes wrong, just die. Right? Flat out die. Unless someone else deal with the problem. But if you apply that on a recursive level, that I will show you more in detail just in a second, is actually very powerful. And a very simple model that scales across all complexities, which is also very important. Most of us write distributed systems today, even though we don't want to, because we have to, right? And then it's very important to have very simple individual rules that can be understood at large scale as well. And I really think that we need a way out of the stage tar pit. This is also a link. I had links to all the papers down, but I had to scratch them out because of the translation. But as I said again, they are at the end. You know, almost all failures relate to some sort of state. Inconsistent state, or inconsistent data, partial data, wrong data, reordered data, duplication of data, all kinds of data being in not the format or way you want. Okay? So if we now try to classify data or state, and what it means, this great paper out of the tar pit defines it as we have two types of state. We have input state, and then we have input data, and then we have derived data. Okay, so input data is data that's given to you from the outside. That's data that you can't reproduce. If you lose that, you've lost it. I mean, unless you go out, for example, to the customer, ask him to fill in the form again, or type in his email address or whatever it is. Like if you lost it, you lost it. Okay, and then we have derived data, the data that you can actually derive from existing data. That's data that you can recompute. But it's the input data that is the critical one. That's the thing that you just simply cannot lose. Sure, you can store it in database. The database will also go offline and so on. So state is a problem, right? And we need a good way of managing and thinking about it. And you know, in traditional state management that most of us have written like through our careers, it can look something like this. And I'll try to explain this diagram. I can't really see everything here, by the way, because it's sort of. But it doesn't matter. The client here is this white ball here, or circle, or object, and then you have the blue one represents some sort of object in the system, some sort of service or class or whatever, yes, class instance or something like that. And then you have this red square that represents critical state that needs protection, critical states that we just cannot lose. That was given to us from someone. Some other service, some client, something that we just can't simply lose. And then we have the red dotted line there. That is the thread boundary, and I'll get back to why that's important later. Okay, so we have a bunch of scattered objects here, all connected in some sort of network. Okay, so now let's see. The client comes in and makes a request to one of these components. And the request trickles, continues down into the system. Now, it usually does so in traditional software, you know, writing things in Java, using JEE, for example, so on. It usually does that through a synchronous dispatch mechanism. Every call is made synchronously, all the way down to the component that we are calling down in the end. Right? It might be you go through authentication and authorization, and then down to whatever filtering, and then down to the real component. I don't know. It doesn't matter. But the problem now with this synchronous call chain is that it's very strongly coupled. So if now something goes wrong down here, well, what happened? I pushed the wrong button. Sorry. There we go. If something goes wrong here, the whole call chain likes blown. You have this cascading failure all the way up into the client. So the error is like thrown straight into the client's face. And what should he do with that? He doesn't have a clue why something failed all the way down into the object hierarchy. It doesn't make any sense to throw that straight into the client's face. It doesn't make any sense for have the failure of one component taking down half of your system on the way up to the client. It just doesn't make any sense. So I really think that the way that we have been taught to write systems for too long is really utterly broken from the ground up. We need a better way of dealing with failure management. We need a way of isolating failure management and not having it cascade all the way through. Because as Sidney Dekker said, accidents come from relationships, not broken parts. This is from a great book he wrote called Drift into Failure, where it talks about failure management. It doesn't talk much about software at all, actually. Rocket ships and stuff like that, but it's an interesting book. So my requirement for a sane failure model is that failures, they first need to be contained. Okay, contained means they should not leak. They should not spread like without any control. Okay, they need to be reified. That's sort of turned into a thing, materialized into a thing that you can touch, that you can actually into an object you can send around, that you can reason about. Not just having some failure, leak in some random fashion. Then they need to be able to be signaled. It needs to be a way for the failed component to tell the world, I'm not spreading my disease, but here I'm sick. Can you please help me? Essentially, and so then it also needs someone to be able to observe that signaling. Someone sitting there outside a failed context and being able to manage that, right? And it all boils down to having loose coupling between these components, having a way to materialize the failure and send it somewhere to someone that sits there safely. and you can just observe without being worried, you know, without being affected by the failure. So the first thing we need to do is to contain the failure, okay? Avoid it to leak, avoid it to cascade. The key here is we need compartmentalization. And here we have a lot to learn from the ship industry. They have really applied this bulkhead pattern for years, you know, where they have in the ship you split up the ship into individual compartments. So if one or two or three of these compartments are ripped open for some reason and start being filled with water, the whole ship is still fine. It can actually continue to sail or to move on to its destination. And someone always brings up, you know, what about the Titanic? It obviously doesn't work that well. You know, the Titanic is actually a great example of bulkheading gone wrong. It's actually a great example of cascading failure, because the Titanic didn't have these walls go all the way up, actually. So when enough compartments were ripped open, the ship started to tilt. Water started filling over from one compartment to the next, to the next, to the next, to the next, until all of them were filled with water and the whole ship sank. It's extremely important to have isolation being bulletproof. The system should not leak its failures. Okay? And even though, I think this is also a great example of fault tolerance, right? Because as I said, the ship can continue to sail on with 3 of these compartments filled with water. But we can do better. We can actually heal these compartments. We can bring in resilience that is beyond fault tolerance here. Okay? But that is not sufficient, right? We can't just contain the failure. We need a way to have the failure to be signal, observe, and manage, right? We need this idea of a supervisor. Hopefully not an angry guy like this, but some sort of supervisor that can sit there and observe and manage the failure as it happens, to restore full functionality. And one really great example that I've been using, I think illustrates this idea more, is the idea of a vending machine. Right? You guys love vending machines, I've learned. They're all over the place, right? I actually start to even to enjoy your cold green tea. But my wife can't stand it. So here you have this vending machine. You have this programmer, and you have this coffee machine, and he's been coding all day. He's really eager for coffee or green tea. And he walks up to this, and let's say that this coffee machine takes, 2 coins of whatever currency. And the program puts in 1 coin, presses, I want my coffee, and the machine responds, as it should, add more coins. Okay, the program has not fulfilled his part of the deal. You know, 2 coins you get your coffee, not 1. Okay? So the program puts in 2 coins and he gets his coffee. Everyone's happy. But now the next day he comes in here and he says, I want my coffee. I put in 2 coins now. I'm expecting my coffee. And now he gets like an out of coffee beans error thrown in his face. What should he do with that? I mean, where's the coffee? I mean, where do I even open this machine? I mean, it doesn't make any sense. He can't do anything useful with this message, right? Instead, the way it works, the way at least it should work, I guess, is that at least in a big building you have this service guy that runs around and services these coffee machines, and he gets some sort of signaling through his telephone and an SMS, text message or something like that, saying this coffee machine is down. He should get this error, not the programmer. He should run down and fix the machine, and adding more beans in this case or whatever, fixing, the jammed grinder or something. And the programmer gets his coffee. He didn't have to think about what the problem was. He shouldn't have to think about what the problem was. He just wants his coffee. And he gets it, right? This is really the way we should design software, I think. We have the client, he makes the request, and the service responds with a response, right? Now, if the client is not fulfilling his part of the contract or the protocol of the service, then a validation error should be thrown straight in his face. Okay, so here I'm distinguishing between errors. Errors, in my world, is something that the client should be responsible for dealing with, okay? But if there is a failure, some sort of application failure, that's not the client's responsibility. He shouldn't even see that. He might get notifications that things are delayed because we're doing wrong, we're cleaning up here, or we're trying to, or something like that, you know. That could be nice, but he shouldn't be thrown the error, and please deal with this. Still, that's how most synchronous systems are built today. Instead, applications failure should be sent up to the supervisor guy that sits there in a healthy context, managing that component, and can now deal with it. He can restart him, he can resume him later, you know, he can delegate the request to some other machine, perhaps even, that he knows there's a backup here that can be replicated to, or he can actually, I don't know, send a report to some ops guy, whatever, you know. He can handle it in whatever way he wants, but it's not the responsibility of the client. Okay, and this is really so the idea here can be applied recursively in what I call the onion layer pattern here. The error kernel pattern. The error kernel is not the best name, but it's what has been used in the Erlang community that's been building a lot of these type of systems for 20 years. We have a lot to owe, actually, you know, Joe Armstrong and the Erlang community for coming up with a lot of these great ideas, and they called it the error kernel pattern. Okay. So the idea of the error kernel pattern, but by the way, I can just show you that the idea is that you have this innermost, you know, center here where your critical state belongs. I'm going to illustrate it just in a second. And then you have these layers of defense that protects your application from the hostile world outside, essentially. That is why I call onion layer. And the interesting thing is that whenever a request hits the innermost center of this onion, or your application, then you can always assume correctness. You can always assume that this will never fail. It's been validated, it's been vetted, or whatever it needs. Like all the services and the needs are up and fine, and everything is fine. You know? But along the way, things might fail. Okay? So here is an example then of the same sort of idea, but here we have onion layered state management instead of traditional state management. And we have the same legend here. The blue box here is the blue ball here is like some object in your system, and so on. And this red box here represents state you can't lose, right? That is the state we put in the center in what we call the error kernel. Okay? We can always assume that when a request hits the error kernel, things are correct. We don't have to worry anymore. And we do that by adding layers of protection, layers of defense, essentially. As soon as there might be some risky thing involved in an operation, we never do it ourselves. That's way too risky. I don't want to die. We delegate to some poor guy that will have to run out of the minefield, and he might get blown up, but that's fine. I can just create a new one, right, to do the same request again. If you want to take sort of a not politically correct view at it in a way. So then you have these. So you lay out your sort of your objects in this hierarchical level, in which each component acts as a supervisor and creates the components it's using. Right. So you have this graph in which each parent manages the child. And managing here means actually responsible for everything, including not just starting and stopping, but also failure. Okay? And the interesting thing is the only way we can make that work is to have the thread boundary being around each of these objects. Not per request, because that leads to cascading failures. But around each object, each of these runs in its own thread. There are many ways you can do this technically, right? In an efficient fashion, of course. You can do multiplexing. You can like 4 threads, one run 1 million of these that take turns running. It doesn't sit and own the thread necessarily. It can, right? If you're the disruptor, for example, Martin Thompson's great LMAX great framework. It actually sits on the thread and pins on the thread just for efficiency. On the other hand, you can just have 4 of these objects on a 4-core machine. But in Akka, for example, we use multiplexing here. So we take turns. There's a scheduler that's scheduling these. But the important thing is that it all runs in a thread in full isolation. So if it fails, the thread blown up, but the failure doesn't leak. No one else is affected. 5 minutes left. Okay. So now, if we take an example here now, you can't really see. There should be this white client here. He makes a request to some of these objects, you know, from the underneath here. He never makes a request directly up. You always need to go through these layers, you know, this level of defense. So now let's say that this component fails. You know, then an error is signaled up to Supervisor here. That gets notified, okay, something went wrong here. I know exactly what went wrong. The failure is reified and sent to me. I can act upon it. He can, in this case, you know, just restart the component, resume the request, and return to the client. The client didn't even find out that the system actually went down. It just continued operating, and it was healing itself. And there might, of course, be situations where an error actually hits all the way up to error curve. For example, if it's an out of memory in Java, there's nothing really you can do about that. It will hit the error curve and take down the whole JVM. But then it's extremely important that this doesn't just run on a single machine. But you have a mechanism of having this spread out on multiple machines. So the error can actually track, or the reified error can actually signal across the network to some other part that can, on another node, that can take over. And this is all something that needs to be provided by a runtime. Akka has this out of the box, for example. And we have fully embraced this way of thinking. So if you remember the meerkats, this is actually exactly how they were operating. The dominant female is extremely important to the group. She never does anything herself. She's sort of the error kernel. She always delegates dangerous work to subordinates and then gets notified, things are fine. I can, as in this example, cross the road safely. Okay? It's also almost exactly how the world works today, right? In everyday life. We have these layers of protection. We don't think much about them. But our whole world is like built around this onion layered failure model in a way. And it takes quite a lot of failure to reach all the way down to us as individuals. I mean, the shortage in food markets, you know, or like oil markets in the world might somehow affect you, but it won't like kill you, right? And it will take quite a lot of failure to bring it all the way down to that there's, you know, starvation in the country, for example. It happens. It's really sad, but it happens. I really believe this is also, I mean, a great model for thinking about software, as I've tried to illustrate. So, to sum things up, one of the key takeaways here, I actually have two, and that is a complex system, they always run as broken systems. In the complex systems, like most of you I'm sure are writing today, something is always failing somewhere. And that's the way it's supposed to be, right? There's nothing wrong about that. Embrace it. And make sure that you fully embrace resilience by design, right? Design for it, think about it from day one. And it's not that scary, actually. So, without resilience, nothing else really matters. That was all I think I had today. Thanks for listening. Here are all the references if you want to dive into some more about this. Thank you.
Thank you for the great talks. Your example, Supervisor, is fully passive. All failure has to be reported, right? But I'm not sure my idea is not effective or not, but how about active supervision? what,
What do you mean, like checking in on it?
yeah, checking in.
Yeah, I'm sure, but I'd say that's often how it actually is implemented, especially in a distributed system. It's usually implemented by checking in. So the idea, I mean, the simplest idea is that you will be notified. But if a node is down, how can you be notified? You can't ask him if a node just vanishes, from the plan. And then you need to use polling, some sort of. And in Naka cluster, we use heartbeat. And then all nodes do heartbeat around the system. So if a heartbeat is missing, or n number of heartbeating, 5, 10 for a while, then you can assume the node to be dead. It still might be up. It might be just a temporary network drop. He might be being overloaded now, right? Go on his knees. It might not be fair to just say you're dead. But that's the best way to deal with it, right? And if it then comes up, you need to go through the regular join procedure. So it's often a combination, I'd say.
Okay, thank you.
時間なので、後で懇親会なのでまた質問する機会がありますので、そちらのタイミングでお願いします。
If we don't, please grab me afterwards. I'm here the whole day. Unless we have time for more questions. We can take them outside then.
Yes. Jonas.
Okay. Thanks.